Alright, welcome everybody to AP Calculus. We're on section 2.4. In this lesson, we're going to be talking about continuity. When is a function continuous and when is a function not continuous? So in this example, you're seeing four different pictures at x equals c when the function is discontinuous. So in the first example, go ahead and write this down. We have f of c. And let's just zoom in a little bit bigger so you guys can see this clearly. So we have f of c is undefined. And basically what we're saying is at x equals c, there is no y value. Let's see if I could get my pointer to be on the go, on the ready. So at this particular c value, since it's an open circle, there is no y value. F of c is undefined, and so that's what we're saying. F of c is undefined. At this next particular graph, this function is also discontinuous because from the left side of the graph, you're following the function, and then there's a break in the graph. There's this, we call this a jump discontinuity. There's a break in the graph. And so this function does not continue, it's not smooth. You have to lift up your pencil to go from one part of the graph to the other part of the graph. So what we're going to write is the limit as x approaches c of f of x is undefined. And so what we're saying is the limit from the left is not the same as the limit from the right. In the third example, we have that f of c is undefined. And the limit as x approaches c of this function, let's call that function f of x, is also undefined. And let me get my pointer for you guys. So what we're saying is, if you follow the red graph, from the left side, as you approach c, your y value is going up to infinity. From the right side, as you approach the x value of c, the graph goes to negative infinity. So you have one part of the graph, the right side, going down, down, down to negative infinity. Then you have the left side of the graph going up, up, up to positive infinity. So we don't know what the answer is. Is it positive infinity? Is it negative infinity? We don't know. We say the answer, the limit, we say the limit is undefined. And in our last example, go back to our pen here, we have that the value at c does exist. So f of c exists. Right, and that's the filled in circle. We could say this y, let's get a different color. Let's say that the y value at c is f of c. Whatever that y value is, it's f of c. That'll give us the y value. So f of c does exist. However, the limit also exists. Even though there's an open circle, from the left side and right side, we're going to the same y value. I'll show you that in a moment, but we're going to say the limit as x approaches c of that function f of x also exists. That's nice. So the value at c exists, the limit exists. However, and let me just move this a little bit to the left side. So there's a however. We're gonna say, but f of c does not equal to the limit as x approaches c, move this a little bit more to the left, of f of x. So if I go back to my pointer, let me just zoom, there you go. So in the graph you have that at c, the y value is f of c. So we know that function is defined. At c, the function has this filled in circle, that's the y value. However, the limit, if you follow the graph from the left side, you're approaching a different y value. Whatever this y value is, where the open circle is, that's what the limit is. From the right side, you're also approaching a different y value than f of c. F of c is up here. The open circle is down here. And both parts of the graph are approaching that open circle. So even though the function exists, even though the limit exists, the function is still discontinuous because the function at c value does not equal to the limit y value. So this is a different way of looking at discontinuity. So here we have 4 different examples of looking at a discontinuous function, and for continuity to happen, in order for a function to be continuous at x equals c, you have to have the following conditions. The following conditions are need to be satisfied. So the first condition is f of c has to be defined. F of x has to be defined. The function, as you can see in this example, everywhere along that function, there's no break, there's no hole, it's just a smooth continuous curve, and there's no breaks in the graph. So this is a continuous function. You never have to lift up your pencil. If you're drawing this red line, you never have to lift up your pencil, and you can just, or pen, and you can just draw that. So that tells you that the function is defined everywhere. The limit exists. That's how you know you have a continuous function. The left side this left side limit is also the same as the right side limit, and we're going to look at some examples in a moment. And number 3, the y value has to equal the limit. The y value, the function has to be defined, and wherever that function is defined, it's the same y value as the limit. So let's see if we have some examples coming up next. Alright, nice example right here. So the question is, discuss the continuity at the following x values. Is this function continuous? As you look at the graph, do you see some holes in the graph? Maybe some places where there's like a break in the graph. Maybe there's a place where if you were drawing the red line, right? If you're drawing the red line, you have to at some point lift up your pen or pencil to continue drawing the red line. And if that does happen, that tells you that the function is not continuous at that particular x value. So let's look at x equals 0. At x equals 0, is the function continuous? At x equals 0. Alright, so let me get my pen here. And actually, let me just show you where at x equals 0, this is the x-axis. At x equals 0, we have this closed fill-in circle where y equals 6. At x equals 0, y equals 6. So this is how we write it in calculus. For letter A, x equals 0. We're going to say, I'll do this in green. We're going to say f of 0 is a function defined at that x value. Yeah, it is, and the y value is 6. So the function is defined. So that's the first step. There's 3 steps to this. Step number 2, does the limit exist at x equals 0? Does the limit as x approaches 0 of that function, does it exist? And it does. The answer is 6. So not only is the function defined at 0, check, 6, the limit exists, check. The third question we ask ourselves when we're looking at continuity is, does the function value, in this case f of 0, let me move my blackboard to the left a little bit, does the function value equal to the limit as x approaches, in this case 0, of f of x? And the answer is yeah, 6 is a function value at 0, and that's the same as the limit. Therefore, f is continuous. Your function is continuous. Alright. Maybe we should be just a little bit more specific. Continuous at x equals 0. You know, with calculus, you gotta be precise. Like, where exactly are we talking about? So, at x equals 0. Letter C. So now we're looking at x equals 3. So if we look at x equals 3, we're gonna ask ourselves the same 3 questions. The first question is the function defined at 3. So in other words, what's f of 3? That's the first question. Is a function defined? F of 3 is, looks like it's 1. Like the y value is 1 if you follow the y value. So we know the function is defined. The answer is 1. That's the y value. Number 2. Does the limit exist? Does the limit at x equals 3 does it exist? And the answer to that question is, let me get my pointer for you. From the left side of the graph, the limit is approaching 1. But from the right side of the graph, the limit is approaching 2. They have different y values, different limits from the left and right, so the limit does not exist. At that point, since the limit does not exist, you can just say the function is discontinuous. You don't have to go to the third case, you're just done. You can say the function is already discontinuous. So since the limit at x approaches 3, does it exist? I'm going to put a question mark, and we're going to say does not exist. T and E does not exist. Therefore, function is, we're going to say function isn't continuous at x equals 3. Alright, that's letter C. Letter D. And I realize I might need some more space, but hopefully we can make it work. Let's see if I could maybe do D somewhere else. Give me a second. Let's see if I could just cross this out. Nope, that's not gonna work. Let me try one more time. Nope. Okay, so I was just trying to delete that little part right there, but it's okay. I'll make it work. At x equals 5, is the function continuous? So notice at x equals 5, let me get my pointer. From the left side of the graph, you're approaching negative infinity, but there's an asymptote, and that's what this little blue dashed line means. In other words, the red line will never become the other side red line. So at that point, we could say that at x equals 5, the function is undefined, right? We don't know what the y value is. You might say negative infinity, but can you tell us what the y value is? We don't know what the number is for negative infinity, so we can just say the function at 5 is undefined. So that's all we're gonna say. F of 5, the function at 5 equals undefined. We don't know what the y value is, and so therefore f of x is not continuous at 5. This function, we could say your function, you could just say f, or in this case we could say f of x if we're talking about a function in terms of x. F of x for this particular example, don't get confused with the other one. F of x isn't continuous at x equals 5. Alright, last example, letter E. Let's look at x equals 7. Move the graph down just a little bit at x equals 7. So in this particular graph at x equals 7, if you're looking at your 3 conditions for continuity, the first condition is the function defined at 7. What is f of 7? And the question is, we don't know. It's undefined. There's an empty circle. And since the function is undefined at x equals 7, we can say the function is discontinuous. So there's these breaks in the graph, there's these holes in the graph, and that allows us to know that a function is not continuous because of those breaks, because of those holes. There's these different types of discontinuity. Let me point some of them out for you. This right here, with both of the red lines are going down to negative infinity, that's called an infinite discontinuity. At this point, where the red line at x equals 3, let's say at x equals 3, where you go from one filled in circle to an empty circle, this is called a jump discontinuity, because you have to go from one part of the graph to another part, and that's called a jump discontinuity. Here, where you have this open circle, that's called the removable discontinuity. A removable. In order to have this red line be continuous, in order to make it continuous, you would have to put back whatever you removed from the hole. So whatever's being removed, you would have to fill it back in. So that's called the removable discontinuity. Alright, that was just some vocab for you. Now we're gonna finish off our little example here we're gonna finish off our notes with our couple more examples here. Alright, so in this next example, we're gonna discuss, let's hide this pen, we're gonna discuss the continuity of the following functions. So in the first function, 1 over x minus 3, right, you have part of the red line on the left side of 3, and that red line is not a continuous red line. The other part of that red line is on the other side of that 3. So we say that this function is discontinuous. So this is how we could write it. Since f of 3 does not exist, right? The values are, there's an asymptote at x equals 3. Since f of 3 does not exist, f is a function not continuous. F is not continuous at x equals 3. Now in this next example, you have f of x. Actually, let me just well, let's call it I want to give it a different name, a different function name. So let's see if I can erase. Can I erase this? Yay, I can erase. Okay, good. I just wanted to call it some other letter for purposes of calling it a different function. So let's call it g. Function g. So g of x equals x plus 3 over x squared minus 9. That's the graph. Kind of looks like the f function graph, right? You have part of the graph on the right side, and there is that part on the right side. You have part of the graph on the left side. The only thing that's different about this graph is that you have this little piece, right? There's a little hole right here. And the question is, how is it that we have this little hole here when this g function kind of resembles the f function? So let's show you guys the algebra to this. Let's show you the math to this. So here's the work, you guys. For the g function, you could still have the numerator, and the denominator you could factor that out. X squared minus 9 is the same as x plus 3, x minus 3. If you factor it out, x plus 3, x minus 3. At this point, you could cancel out the x plus 3's, the one on top and the one on the bottom. In other words, you could remove the x plus 3's. And when you remove the x plus 3, that's how we're ending up with this open circle right here. Because what will make this function undefined is when x equals to 0. When you have a 0 on the denominator, that will make the function undefined. So what is that value? When will you get a 0 in the denominator? Well, if you're solving for x, that's when x is equal to -3. So when x is equal to -3, that's a problem. However, when you factored it out, you were able to cancel out that problem. You were able to remove the problem. And so that's a removable discontinuity right there. That empty circle is a removable discontinuity. And then the graph, the g function, begins to look like the f function, where you have not only a removable discontinuity, but you also have an infinite discontinuity. So these are just some different types of discontinuities here. And the g function kind of looks like the f function when you simplify. So we end up having 1 over x minus 3, just like the f function. Alright. And finally, as we finish up, a couple more examples. In this example in blue, you have 1 over x minus 2 to the third power. And the question is this function ever discontinuous? What will make this function discontinuous? So the question is, could you ever get a 0 in the denominator? So x minus 2 to the third power, could you ever get a 0? Well, I mean, mentally, if you just look at the problem, when x equals 2, 2 minus 2 is 0. 0 to the third power is already 0. So by mentally, you could just say x equals 2. That's how you get a 0. But if you wanted to solve, just set the denominator equal 0. I guess you would do the cube root on both sides. Not needed because we already did mental math, but anyways, x minus 2 equals 0. My writing is not showing. No, I'm not sure why. Okay, x minus 2 equals to 0. Then x is equal to 2. So that's where the denominator equals 0, and that's where the function is not continuous. So another way of saying where is a function discontinuous, you could say f, the function, is continuous. Let me fix my spelling. It's U-O-U-S. The function is continuous everywhere except, I think because I don't know why my pen is not showing. Everywhere except x equals 2. So by saying that word except, you're saying function not continuous at 2. Alright. In the next example, there is no fraction, there is no denominator. So this cubic function, if you recall from Algebra 2 of your knowledge of functions, a cubic function might look like this, where there's no holes, breaks, or graphs. There's no holes or breaks in the graph, so we say the function is continuous. So that cubic function is continuous. So in that example, we say f is continuous. F is continuous. Why not? Say everywhere. Continuous everywhere. Alright, and that's everywhere. In the third example, 6 sine 3x, this trig function is continuous. So, and you could graph it on your graphing calculator. You'll see that it's a sine wave, sine curve. F is continuous. Alright.